So I think an important place for us to start is revising and making sure that we know everything from grade 11 that we were supposed to know. Okay, so the first thing I'm going to do is I'm going to start on the Cartesian plane. And I want to point out to you, you've got a set of axes, an x-axis, which is a horizontal axis, and a y-axis, which is a vertical axis. And we know that that cuts the Cartesian plane into 4 distinct regions or areas referred to as quadrants. All right, so this one over here in the top right-hand corner, this is always quadrant number 1. And then to its left, this is always quadrant number 2. And then here below, this is always quadrant number 3. And then down here on the right-hand side, this is always quadrant number 4. The other thing that mathematicians decided at some point in the past is that we would use this over here as 0 degrees. And because this is a right angle, this up here ends up being 90 degrees. Then because this is a straight line, because we've added another 90 over here, this ends up being 180 degrees. And then I'm just going to have to move this down a little bit. This ends up here being 270 degrees because we've added another 90. And then over here, we end up back where we started, which is at 0 degrees or 360. Okay, so in other words, we have done a full circle. Let's just get rid of, oh gosh, no, hang on, undo. All right, that's not what I wanted to do. I wanted to get rid of the little degree signs, those little things over there. Okay, there we go. All right, now the other thing that is super, super important for us to remember in trigonometry is the signs of x and y in each quadrant, right? So in quadrant number 1, can anybody tell me what is the sign of x and y in quadrant 1? Isaac, Anya, welcome. Nice to have you with us. The signs of x and y, the signs of the variables? Positive, absolutely. Thanks, Cassandra. Thanks, Panita. Who else said something? 27608. I don't know who that is, but you're right. Everything is positive, quite right. So we have a positive x coordinate. We have a positive y coordinate. All right. And then when we go into quadrant number 2, which one, x or y, changes sign? Which one becomes negative?
X.
X, quite right. Okay, so when we are in quadrant 2, x is negative, but y is still positive. So y is positive above the x-axis. All right, now we're going to pop down into quadrant number 3. And here we find that both x and y are negative. And when we eventually get into quadrant number 4, we find that x becomes positive again and y remains negative. So it's safe to say that x coordinates are positive above the x-axis. Sorry, y coordinates are positive above the x-axis. Y coordinates are negative below the x-axis. Right, to the left of the y-axis, x is negative. To the right of the y-axis, x is positive. Now, these x's and y's are really, really important in trigonometry. And the reason that they're super, super important is trigonometry is because this is how our ratios are made. So when we talk about sine theta, in terms of x and y and one other variable, what is sine theta equal to? Can you remember from last year? What is sine theta equal to? You can either unmute or pop it in the chat. I've got to use an x or a y. That's it, Panita, y over r. All right. What does r represent, Panita?
Hypotenuse.
Absolutely, the hypotenuse. Okay, or the terminal arm. All right, and I'm going to talk a little bit about the terminal arm now. But I just wanted to bring this up first. And then cos theta, how can that ratio be described? That ratio is x over r. Good, Kanyesile. Nice. And then our last ratio, tan theta, and that is described as, anybody tell me? Y over x. Good, Kanyesile, lovely. Okay, and it's really important, Matrix, that you know this in terms of x and y and r rather than o and a and h, which is what we teach you in grade 10. Okay, so these are our ratios. Sine theta is y over r, cos theta is x over r, tan theta is y over x. And this is why our ratios change sign depending which quadrant they're in. That's why we call this diagram that we're actually working on here, it's called the cast diagram. So the letter C goes into this quadrant, quadrant 4. The letter A is actually in this quadrant over here. S is in this quadrant over here, and T is in that quadrant over there. So have you seen that before? You've seen the cast diagram. I'll just write cast up here at the top as well. Is that something that your teachers have spoken to you about?
Yes, ma'am.
Yes, okay, all right, oh good. All right, so you know what the cast diagram is, and the cast diagram is there to tell us which ratios are positive or negative in which quadrants. Well, which ratios are positive. All right, so the letter A, what does the letter A represent? It stands for the word?
All.
Someone said it?
All.
All, yes, Kanyesile, that's right, all. Okay, good, you guys are saying all. Nice, lovely. So all right, and that is because x and y are positive. All right, so x and y are positive, and that's why if we divide a positive with a positive, we're going to end up with a positive answer. Why is r always positive? Does anybody know? Why is r always positive?
Because the value of x and y is also always positive.
Only in the first quadrants you can, yeah, okay? But then
So
in the
in the
other
first
quadrants,
quadrant.
x and y can change their signs. But there's a very specific reason why r always has to be positive. Do you know why?
Panita's got that answer for us in the chat.
She has. She has. So Panita, you said it's because it's a distance. Absolutely. All right. So in this form here, all right, r represents the length of the terminal arm. Right, so it's not on the axes, it's a radius. Absolutely. Okay, so what we have is we have an arm that is anchored at the origin, like the minute hand of a clock. Right, and I'm going to try and do it with a highlighter rather than another color. Let's use yellow. So this is the center over here. All right, and your terminal arm lies on the axis, right? And it is anchored here at the origin. And just like the minute hand of a clock, this arm can swing, all right? We're going to talk about it swinging now, but because this over here represents the distance from O to the end of the terminal arm, we call that R. Okay, so R is a distance. It is the length of the terminal arm. And because it is a length or a distance, it is always, always, always positive. So this arm can swing up and it can come to rest somewhere here in the first quadrant. But in fact, it could come to rest in any quadrant. So it could come to rest in quadrant number 2. Now, what we need to be careful of is that when we get into quadrant 2, the sign of x changes. So whilst we still have sine theta is positive y over positive r, as far as cos theta is concerned, we've now got negative x over positive r, and that's why cos is negative in the second quadrant. Same thing with tan theta. Tan theta is a ratio of y over x. So if I take a positive number and I divide it by a negative one, I will get a negative outcome. All right. Everybody happy with what I've said so far? Is there anything here any questions?
No, ma'am, no question.
No, we're fine. Okay, we're just going through all the basics because without this, we can't do anything. All right, then we get into the third quadrant. All right, and now we end up with sine theta is negative y over positive r, and cos theta is negative x over positive r, and tan theta is negative y over negative x. And we know that when we divide a negative with a negative, we end up with a positive answer. And that's why we've got the letter T in the third quadrant, because tan theta is the only ratio that is positive. I forgot to say it over here in quadrant number 2. Can you see it's the reason we have an S here is because sine theta is the only ratio that is positive. And then we end up over here in quadrant number 4, and sine theta is negative y over r, cos theta is positive x over r, and tan theta is negative y over x. And that's where the C comes from. Okay, so the C stands for cos theta. So the cos diagram tells us which ratios are positive in which quadrant. All right, very, very, very important. You just check what's going on in the chat. Everybody's happy. All right, lovely. So now let's talk a little bit more about this terminal arm and its ability to swing around the origin. All right, because we people have decided that 0 degrees, let me just highlight it where you know that already, that 0 degrees is over here and 90 degrees is up there and 180 is over there. We have decided that when the terminal arm swings in an anti-clockwise direction, then angles are positive. So in other words, if the terminal arm is going in that direction, all angles are positive. Okay, so if I go all the way up to here, it's seen as positive 90. If I go around to here, it's maybe seen as a positive 120 or whatever the case is. Angles are negative when I change direction. So there's a link to science here. All right, so we have decided that positive is one direction, anti-clockwise, and therefore when we move in the other direction, we give that the opposite sign. All right, so in other words, if my terminal arm started again at the origin, but it went in this direction over here, and it came down here, that would be seen as a negative direction. So angles will be negative. Okay, when I go in a clockwise direction. And that should make sense because if I'm starting at 360, it's getting smaller, isn't it? So angles have to be negative because I am reducing the size of the angle. So as 360 approaches 270 and 180, things are getting smaller. Does that make sense to everybody? So don't be scared of angles being positive or negative because it's simply an instruction on which direction the terminal arm needs to move. Okay, so now let's get into our reduction formulae. I think what I'm going to have to do is clear some of this stuff off here, otherwise it's going to become a little bit confusing for us. I'm also going to get rid of those because we've spoken about that and I think everybody knows that by now. All right, so when we are in quadrant number 1, this is where angles are acute. Okay, so all angles that are acute are seen as being smaller than 90 degrees, right? So when we talk about theta specifically, all right, we're talking about an acute angle, but so we don't need to reduce because the whole idea behind reduction formulae, the word reduction means to make something smaller. So what we are doing is we're taking angles that are obtuse or reflex or bigger than 360 and we are writing them in terms of an acute angle. So when an angle is acute, there is no need to reduce because it's already reduced, all right? But we may need to use reduction formulae. So for the first quadrant, we can go plus 90 degrees in an anti-clockwise direction, and then I can come minus theta degrees in the other direction. So what I've done here, right, is, don't want to delete that, is I've done this. I've gone from this position over here in this direction up to 90, and then I have changed direction, and I have ended up with my terminal arm being located somewhere inside quadrant number 1. Okay, I don't know exactly where because I haven't got a definition for theta, right? So reduction formula for quadrant number 1 is 90 minus theta, and this is super important because you learn about sine 90 minus theta and what happens there, and about cos 90 minus theta and what happens there as well. Now, before I get into what that becomes, I just want to show you something else here on the side. Okay, I am going to draw a very badly drawn right-angled triangle. Okay. Now, if this angle over here, matrix, is theta, how big is this angle over here in terms of theta?
90 minus theta.
Absolutely. Okay, so this is 90 minus theta. Does that make sense to everybody else?
Yes, ma'am.
Everybody's happy with
Yes,
that, that's
ma'am.
90
Yes,
minus
ma'am.
theta. Cool beans. Right. So now let's say I decide I'm going to give these 3 sides, I'm going to give them names. All right. So I'm going to call this side A, and I'm going to call this side B, and I'm going to call this side C. All right. If I talk about, let's not do that one. Let's do this. Okay. Let's talk about the sine of theta as it relates to this diagram. Okay, so remember, we can only talk about sine in relation to a specific angle. So here we're talking about this specific angle. Remember, the sine of the angle means the opposite side over the hypotenuse. So in this case, sine theta would be equal to what over what?
B over C.
Did you say B over C?
Ma'am, it's A over C.
It's A over C. Okay, quite right. It's going to be A over C. Okay, opposite over hypotenuse. All right, going back to grade 10, right? Now, I'm going to change my perspective, right? And let's say I'm now working with this angle over here, the 90 minus theta. All right, so now I'm going to write cos 90 minus theta. So now this is my reference angle, the purple angle. And again, looking at my diagram, what is my ratio of cos 90 minus theta in terms of this diagram? It's going to be adjacent over hypotenuse. So it's equal to, in terms of A's, B's, and C's?
B
A
over
over
C.
C. A over C.
Okay. Anyone who's saying
B
A
over C.
A
Oh.
over C, A over C.
Oh,
Okay, A over C. All right. So the reason for that is because remember, the cos of an angle is the adjacent side over the hypotenuse. Okay, so that's why the cos of the angle 90 minus theta is A over C. Right. If I was doing sine 90 minus theta, which I certainly can do, sine 90 minus theta will be B over C. And incidentally, cos theta will be B over C as well. This is where it comes from. Okay, so can you see in maths, if two things are equal to the same thing, then we must conclude that they are equal to one another. So if sine 90 minus theta is equal to B over C and cos theta is equal to B over C, then 90 minus theta must be equal to cos theta. And similarly, if sine theta is equal to A over C and cos 90 minus theta is equal to A over C, then sine theta has to be equal to cos 90 minus theta. All right, so that's where this comes from. Going back here, that's why sine 90 minus theta is equal to cos theta. And it's also the reason why cos 90 minus theta is equal to sine theta. Very, very, very important, okay, for you now in matric. This is something that gets used a lot. And you'll see in context as we sort of progress with these lessons why this is so very, very important for you. Okay, so please, 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 everything that we're going through today, make sure that you learned all this stuff off by heart, because your reduction formulae and the cast diagram and all this sort of stuff is not information that's given to you. Okay, some of the formulae are given, but this information here, it's presumed that you will know this. All right, any questions at this stage? Anything that I've said that you want to ask about?
No,
Sure,
ma'am.
guys.
Thank you. No,
No
ma'am.
problem. All right, lovely. Now, let's imagine, all right, this terminal arm of ours, okay? Instead of it going up to 90 and then back by theta degrees, let's pretend it's lying here again. Ah, man. I'm going to figure out how to stop doing that. Okay. All right. It's lying here again. All right. And now it's going to swing all the way up to 90. And then it's going to go theta degrees forward into quadrant number 2. Can you imagine that? So up to 90. And then it's going to go theta degrees forward. So now it's ended up over here. All right. So I can also, well, there's two ways I can get into the second quadrant, but one way I can get into the second quadrant is by saying 90 plus theta. Remember we said when angles are positive, we're moving in an anti-clockwise direction. So that's why it's plus 90 plus theta. Yes, Precious, what's your question? You're welcome to ask, Precious.
Or you can type it in the chat if you'd rather.
Yeah, absolutely.
All right, well, we're not getting a response. Maybe we'll move on and I'll let you know if we do have.
Okay, thank you. Thanks, Coco. You're a star. All right, so just like we had sine 90 minus and cos 90 minus, so matrix, we have got sine 90 plus, and we have got cos 90 plus. All right, now let me just clear a little bit of space here because I'm going to be writing in the way. All right, so now what are these equal to? Okay, so remember, the output takes the sign of the original function. So if we're talking about sine 90 plus is quadrant 2. And sine theta is positive in quadrant 2. So what comes out, cos theta, is also going to be positive. As far as cos 90 plus theta, and this is the one that we really need to remember, cos theta is negative in quadrant 2. All right, so our outcome is negative sine theta. Okay, very, very, very important for you going forward. Everybody happy with that? I presume so until I hear otherwise. All right, so we've got into the second quadrant now. We've done it first of all by saying 90 plus theta. But the other way that we could get into the second quadrant is by going all the way plus to 180 degrees and then going theta degrees backwards. So what happens here is our terminal arm Right, let's pretend that this is our terminal arm. Our terminal arm swings all the way around and it now comes to lie flat over here. Right, so in other words, what it would have done is it would have done 180 degrees. Now, if it moves a little bit in this direction, remember when we move in a clockwise direction, we are minusing. So that's why we have the reduction formula here, 180 plus 180 minus theta. Okay, so 180 minus theta is quadrant number 2. That's how we get into quadrant number 2, where all our obtuse angles are situated. And again, we can have the sine, the cos, the tan of this particular angle. So we've got the sine of 180 minus theta, we've got the cos of 180 minus theta, and we have the tan of 180 minus theta. Okay, so again, the cast diagram helps us with this. It helps us to remember which ratios are positive in which quadrant. Okay, so sine 180 minus theta, 180 minus theta is quadrant 2. Sine theta is positive. So this reduces to sine theta. Okay, so the sine of an acute angle. Cos 180 minus theta, this reduces to negative.
Negative.
Cos theta, good Tobile. And tan 180 minus theta, this reduces to
Negative tan.
negative tan theta, absolutely. By the way, this is not something that we generally get asked, but I have seen it in textbooks. I just want to ask you guys a question. If you saw this, I suppose I'm asking you a little bit prematurely, but anyway, it doesn't matter. If you saw this, what would you do? Anybody got any ideas what we would do with that?
We're using the triangle, ma'am.
No, we're not using. I'm just saying, if you saw tan 90 minus theta, all right, in one of your questions, what would you, how would you rewrite that? There's another way that you could rewrite that.
Negative tan theta.
Negative tan theta? I'm afraid not, because remember, it's not going to be negative because tan 90 minus theta is the first quadrant, isn't it? And we know from our cast diagram that it would be positive. Right?
So
anybody
tan theta.
You're gonna I know, as I say, I am jumping the gun a little bit here. Liam, what did you want to say?
Would you turn tan 90 minus theta into sine 90 minus theta over cos 90 minus theta, and then change the signs around, which turns it into cos theta over sine theta?
Absolutely. Okay, so I kind of jumped the gun. That was really, really good. And a lot of you were saying identities and yes, sine over cos. Yes, that's right, Kiket. So very good. Okay, yes, it is an identity, Ordain. You are quite right. All right, so what we would have done here, and as I said, I am jumping the gun a little bit, but I couldn't help myself. Do you remember from last year that tan theta is equal to sine theta over cos theta? You remember that?
Yes,
it's one of our identities, super, super important. So what we could do here is we could write this as sine 90 minus theta over cos
90 minus theta.
That's it, absolutely. Does that make sense to you?
Mm-hmm, definitely.
Okay, definitely. So then the sine of 90 minus theta would be cos theta, and here the cos of 90 minus theta would be sine theta. Okay, just incidentally, this actually, to be honest with you, is not part of the CAPS syllabus, but if you did see it, you would use the tan identity. Anyway, I am coming back to that in a little bit, but as I say, I digress. All right, so now let's go back over here. We've spoken about the two ways that we can get into the second quadrant, 90 plus and 180 minus. So into quadrant number 3 now. I don't want to labor the point here if this is something that you guys already know. I just wanted to be thorough in terms of revising. So now again, our terminal arm is anchored at the origin, and now it swings 180 degrees, and then it goes plus theta degrees forwards into the third quadrant. All right, so the idea is we've gone 180 degrees in an anti-clockwise direction. And now, oh, come on, please stop doing this. Mind you, it's my fault, not the computer's. Okay, and now we've gone another theta degrees forward. So now our terminal arm has come to rest here in the third quadrant, and that's why we've got 180 plus theta, and that represents quadrant number 3. Does that make sense to everybody? So again, we've got the sine of the angle, the cos of the angle, and the tan of the angle. So very important that we learn our reduction formulae, and that we know from the cast diagram that sine 180 plus would be minus sine theta, cos 180 plus would be negative, yeah, it said negative cos theta. And what's going to happen to tan?
It stays positive.
It stays positive. Okay, and it stays positive because a negative divided by a negative is a positive. All right, well, we're nearly there. We almost finished revising the things we need to. There's just a few more things that I need to go through with you. Now imagine, matrix, that your terminal arm has gone all the way around to 270 up to 360, and now it's come back into the fourth quadrant. All right, so to get into the fourth quadrant, we do a full circle and then we go theta degrees backwards. All right, so do you see what I mean? Theta always has to be smaller than 90 in this case. Otherwise, we wouldn't end up in the quadrant that we want to be in. All right, so now we've got the reduction formula, 360 minus theta. All right, and we can have the sine of that angle. We can have the cos of that angle. Ooh, where did the plus come from? I'm writing nonsense here. Okay, minus, and then we've got the tan of this angle as well. Okay, so sine 360 minus theta is?
Negative sine theta.
Lovely, well done. And cos 360 minus theta is?
Positive cos theta.
Positive cos theta. All right, and tan 360 minus theta is?
Negative tan theta.
There we go. All right, well done. That's perfect. Okay, good job. So this is all our reduction formulae, our co-ratios as sine 90 plus and 90 minus are known. The other thing that I just wanted to mention very quickly here is what happens with negative angles. I got so cross with the boys that I teach this year because I kept saying to them, you have to study, and they never studied. Well, the one class anyway. So, but you guys sound like you've been studying and you know all of this in any event. Anyway, so sine, come on, sine minus theta, and cos minus theta, and tan minus theta. Now, if we didn't know what that meant, that could actually be quite scary, right? What are we talking about? I mean, what does sine minus theta mean for us? I mean, in terms of this diagram and the conversation we've had this evening, what does it mean?
It means ma'am is now going in the anti-clockwise direction.
Absolutely. Okay, so instead of us going theta degrees in a positive direction, so in other words, if I've done that and that is positive theta degrees, all I've done is I have reversed my direction and now it's here. Okay, minus theta degrees. Okay, so it's a reflection of the terminal arm over the x-axis. All right, so sine minus theta, cos minus theta, tan minus theta means that my terminal arm has come to rest in quadrant number 4. Okay, so you will see that this reduces in exactly the same way that 360 minus reduces. Okay, so this ends up being negative sine theta. This ends up being positive cos theta. And this ends up being?
Negative tan theta.
Negative tan theta, quite right. Okay, everybody happy with that? Are we all good? Sorry, it's a lot of information tonight, but all of this is so important for where we get started. All right, so the last couple of things that I just wanted to revise with you before we jump in and go and have a look at a couple of questions was we've spoken about the tan identity, right? So this is still very important for you in matric. You will be using it a lot. And there was one other identity that you learned. Can anybody remember what that was? There was another identity.
Sine squared theta plus cos squared
Is
theta.
it sine squared theta plus cos squared theta is equal to 1?
Absolutely. Okay, so sine squared theta plus cos squared theta is equal to 1, and that's referred to as the square identity. All right, so again, with the tan identity, whenever we see tan theta, we write it as sine theta over cos theta. We always do that. But these two are interchangeable. Sometimes we can see 1 and we can write it as sine squared theta plus cos squared theta. And sometimes we can see sine squared theta plus cos squared theta and we can write it as 1. So we've got to be able to go from one to the other. So those are our two identities. The other thing that I also just wanted to mention, all right, is that as far as tan theta is concerned, if you have got tan squared theta, then that will be equal to sine squared theta over cos squared theta. Okay, or if you had, and you're going to see these coming up, if you had tan, you've got to be so careful here, 2 theta, that would be equal to sine 2 theta over cos 2 theta as well. Okay, be very, very careful. You're going to see later, well, it's not this lesson, but later on in the course where we start talking about double angles. So just be careful when you do get to that point. Is that on the formula sheet? It is. Riyadh, no, actually, hang on, I'm talking nonsense. The square identity and the tan identity is not on the formula sheet. Neither is the stuff that I put in the red on the right-hand side. The only things that are on your formula sheet are your compound angle formulae, your double angle formulae, and your sine, cosine, and area rule. The rest of all of this, you have to know off by heart. Okay. So yeah, that's why it's so important going forward that you are able to answer these questions. All right. Okay. So now, all right. Oh yes, Coco, brilliant. Thank you. Okay. Something else to bear in mind. This becomes really important when we start working with proving identities and that kind of thing. Because these are equations, we can make different things the subject of the formula. So if I'm working here with the square identity, I could leave sine squared theta on the left-hand side, and I could take cos squared theta over to the right. So what should I write on the right-hand side? Yes, sine squared theta equals 1 minus cos squared theta, absolutely. And sometimes I might need to factorize what's on the right-hand side. So this bit over here can be factorized. Sometimes I might not need to do this, not always, but sometimes. How would it factorize? Does anybody know?
Ma'am, wouldn't it be one bracket 1 minus cos theta, another bracket 1 plus cos theta?
Lovely, well done. That's excellent. Okay, because it's difference of 2 squares. Okay, so sometimes I may need to write it in this form, or I may not. It just depends. All right, and then cos squared theta is exactly the same thing. It can be written as 1 minus sine squared theta, and then you may find that there are situations where you would need to factorize that as well. It's also difference of squares, so 1 minus sine theta, 1 plus sine theta. Not always, but sometimes. We just have to see, yeah, dots, quite right, difference of 2 squares. We just have to see the situation that we're working in. Okay, so that's pretty much everything that I wanted to revise as far as reduction formulae and identities and positive and negative angles were concerned. I wanted us to go ahead and go and have a look at some of the types of questions. Let me just move these down here, that they would expect us to be able to answer, right? So the first sort of question is one like this. And I also would like to say that until you start solving equations, you are not allowed to use calculators matrix. Okay, calculators are completely banned. I mean, you can use it, like let's say if you want to work out an answer to Pythagoras or something, then you could use your calculator. But you can't use your calculator to answer these questions. All right, so until we start solving for theta or alpha or beta, no calculators. All right, very, very important, because they want to see that we can use the rules, not that we can press buttons on a calculator. All right, so this sort of question is a very common first question in exam papers. And they've told us if sine beta is 2 root 6 over 5 and beta is an angle between 90 and 270, calculate without the use of a calculator and with the aid of a diagram the value of tan beta and sine 90 plus beta. All right, so now the first thing that we need to do is we need to work out in which quadrant we are working, all right? We remember, we don't know, okay? We could be working in quadrant 1, we could be working in quadrant 2, we could be working in quadrant 3, we could be working in quadrant 4. So how are we going to figure out in which quadrant the terminal arm has come to rest? Does anybody know how we do that with these sorts of questions?
So, ma'am, because sine is positive, we should first draw a Cartesian plane, and then we decide where sine is positive, and it's the first and the second quadrant. But because both values are positive, then it should be in the first quadrant. Is that correct?
Okay, you're 100% right, but the one thing that you didn't look at over here was this. Okay.
Oh,
so
right.
because,
Okay.
So because you're 100% correct, because sine theta is positive. Okay, so in other words, this ratio here that I'm coloring in yellow is a positive number. Okay, so you are quite right. That's why it would be this quadrant here or that quadrant there. But they said to us the angle is between 90 and 270. So remember, 90 is here, 270 is there. So telling us the angle is between 90 and 270 is saying to us, well, either we're drawing in quadrant 2 or we're drawing in quadrant 3. So in actual fact, we're going to be drawing this in quadrant number 2. Yes. Does that make sense to everybody?
Yes, ma'am.
You
Yes,
sure?
ma'am.
You all okay with
Yes,
that?
ma'am.
Very, very important to know which quadrant we are working in. Okay, so quite right. Now we have to come along and we're going to draw ourselves a proper diagram. Okay, this just helped us work out which quadrant we were in. And here's our terminal arm. And it was originally lying on its side over here. And then it's swung beta degrees. And now it's come to rest here in quadrant 2. There's the end of our terminal arm. Okay, and it makes a, whoa, what is that? Sorry, I'm trying to draw a straight line, but if that's a straight line, then I'm Mickey Mouse. Okay, that it makes a right angle with the x-axis. Okay, here at the end of the terminal arm, or actually before we say that, how do we interpret, sorry guys, I'm just being an idiot here. Okay, how do we interpret sine beta? All right, sine beta means what? So when we see sine beta is 2 root 6 over 5, how is that interpreted?
Y
It is
over R.
hypotenuse.
Perfect, Tatsu. Okay, it means y over r. Right, so we know that the length of the terminal arm is 5 units. And at the end over here, we know that there is an x coordinate. And we know that the corresponding y coordinate is 2 root 6. Okay, that's what it means. Let's just have a look in the chats. Okay, so Masejo and Miso, you're both saying that you don't understand. What exactly is it that you don't understand? What have I said that you don't understand? But you need to be super specific, okay?
So Lee, so Masero says to me, she does remember, but I don't understand because tan is positive in the third quadrant, and now we're working in the second quadrant. And Masero, that's because they've given us the sine of beta and not the tan of beta, and that is why we're working in the second quadrant rather than the third.
Yeah.
That answers the question.
Cool, thank you so much. All right, so what's missing from this diagram? It is the value of
The value of x.
the value of x, and how are we going to get it?
We do Pythagoras method.
Ah, absolutely. Okay, so now we're going to do the theorem of Pythagoras. All right, so now we come along and we say x squared plus y squared equals r squared. Lovely. Okay, now here, if you do use your calculator, no one is going to know. All right, so this is not the end of the world. All right, so now we need to work out what x squared is going to be equal to. So if someone can please work out 5 squared minus bracket 2 root 6 squared, what does that give us as an answer? It gives us 1. Okay, and now we are going to take the square root. And guys, this is where if we're going to make a mistake in trig, this is where it happens. Okay, remember, we are working in quadrant number 2. We are calculating the value of the x coordinate in quadrant number 2. What sign does x take in the second quadrant?
Negative.
Negative. Okay, so be very, very careful. X can be equal to either positive or negative square root of 1, but because we are in the second quadrant, x is equal to negative 1. Okay, so very, very important. Okay, x and y change sign depending which quadrant you are in. All right, r is always positive because it's a distance. So at the length of the terminal arm, it's always going to be positive. But x and y change sign depending which quadrant you are in. Very, very, very important. So what I like to do with these sorts of Pythagoras diagrams at this stage, and you don't have to do this, but I like to do this, is I like to make a summary. So I say to myself, okay, x is equal to negative 1, whilst y is equal to 2 root 6, and r is equal to 5. Now that I have this information, I can answer any of these questions that they give me. So can you see, Matrix, we've had to do all this work before we've even begun to think about answering the questions. All right, so all of this is super, super necessary before we can even begin answering anything. Okay, so let's have a look at how we are going to answer question A. All right, tan beta. How do we interpret tan beta? It means the tan of any angle is y over x. Okay, so we go back to these normal, yes, y over x, opposite over adjacent, y over x. You can leave your answer as a square root null-wazi, but in this case, because 1 is a perfect square, we don't need to. Okay, so y over x, so this will be written as 2 root 6 over 5. Okay, there's our answer. Next one, B, all right, sine 90. Yes, sorry, can you see it? Ask away.
Ma'am, how is it? Over 5. It's over negative 1.
It's over negative 1.
Oh, sorry, guys. Sorry. My brain. Beg your pardon. At school, I tease the boys and I say to them, I made that mistake on purpose. to see who was paying attention, but I didn't really. Okay, so when we divide something by -1, it becomes negative itself. So we would actually just write this as -2 root 6. Okay, thank you for pointing that out to me. I don't know why I wrote it over 5. Okay, next one, B. Sine of 90 plus beta. All right, so now here we have to use our reduction formulae first. So the sine of 90 plus beta is what?
Cos beta.
It is indeed. It changes to cos beta.
Cos.
Yeah, absolutely. And we're going to get a mark for writing that. So it's very, very important that when we use a reduction formula that we write what we get as a result of reducing. And now what's cos beta equal to in terms of this diagram?
Opposite over adjacent. Hypotenuse.
Okay. So it's equal to x over r. Okay, so try and learn it in terms of x over r. So it's equal to -1 over 5. Okay,
5.
so yeah, so just like there is it's a silly little mnemonic that your teachers may have taught you in grade 10. I don't know if you remember this, SOH CAH TOA. I mean, that's worldwide. Okay, and that's how we remember sine is opposite over hypotenuse, cos is adjacent over hypotenuse, tan is opposite over adjacent. But there's another one that you guys can also work with, and it's SYR CXR TYX. Okay, so sine theta is y over r, cos theta is x over r, and tan theta is y over x. And this one goes shade your rear, cause x rays tan your exterior. Okay, so maybe we could even write that as this way, cause. All right, so the S, the Y, the R, the C, the X, the R, and the tan, and the Y, and the X. Okay, so if you do struggle to remember it, there's just maybe an easier way to be able to do that. Okay, all right, now we come back. We've answered that question as well. So we're happy with that. We've got 5 minutes to go. I was hoping to answer a couple of questions like this as well. Let's just see if we can do the first one, because certainly part A over here involves something that I didn't speak about earlier, right? So they've asked us to simplify these. And again, can you see, without the use of a calculator? So very, very important, matrics, we're never allowed to use a calculator. What do we do in this situation? Anybody know?
You
Let's just see what you guys are saying. Can we reduce these angles? You can. Reduction, absolutely, guys. How would you reduce it? What would you do here? Aha.
And then isn't
No,
it
yes, and Paul, say it.
You divide by 360 and then you multiply by the number in front of the dot with the decimal that you get, and you get your answer.
Okay, so it's a little bit easier than that. You just have to subtract 360 degrees. Okay, so you're just going to take away 360 degrees, because if you take away 360 degrees, you're still going to end up in the correct quadrant, because you would have done a full circle. Absolutely. Okay, but good. I'm glad that you tried. All right, so now really we need to say to ourselves, what is 540 minus 360? What do we get? Exactly, we end up with 180. So what we're allowed to do is we're allowed to write this as the cos of 180 plus theta. Now we see something else that we haven't seen before either. Minus theta minus 180 degrees. There's two ways in which we can look at something like that. first of all, we are multiplying. Now, if you want to, you can factorize. So what you could, if you'd like to do here, is you can take out tan. I'm going to use a square bracket, and I'm going to take out the negative, and then I'm going to have 180, or sorry, theta plus 180. Does that make sense to everybody? Okay. It doesn't matter which order I've written it in. So if I have written theta plus 180, it really is the same as 180 plus theta. Okay, so that's one way. I'm going to talk about the other way just now. I'm just going to draw my divide line, and then here I've got my sine 180 plus theta. Okay, so now I'm going to use my straightforward reduction formulae. Okay, so cos 180 plus theta, what is that going to reduce to, Matrix?
Negative
cos theta.
Negative cos theta. Good, well done. All right, and now, ma'am, why am I factorizing? It's one of the ways in which I can work with tan minus theta minus 180. So I've taken the negative out as a highest common factor. And now what I'm going to do is I'm going to say the tan of 180 plus theta, which would give me positive tan theta. But remember, tan minus theta, so whatever this angle is, it's equal to negative tan theta, right? So this will reduce to negative tan theta. Right, sine 180 plus theta, this is going to reduce to negative sine theta. Good. All right, so now I've got a negative times a negative divided by a negative. So my overall sign will be negative. I have cos theta. I'm going to change tan theta to sine theta over cos theta. And then I want to divide by sine theta. So here, matrix, I can say, because this cos theta is in the numerator, cos theta divided by cos theta is 1, and sine theta divided by sine theta is 1. Therefore, my final answer in this case has to be negative 1.
Ma'am,
Yes.
what happened to the negative after minus tan theta?
Okay, so what happened here is I said that a negative times a negative divided by a negative is a negative.
Oh,
Okay. All right.
Yes.
So I just simplified because I'm going to end up with one term as my answer. So that's why I simplified my signs. Okay. What's also important here is, do you guys understand what I did with this? Does that make sense to you?
Yes, ma'am.
Okay.
Ma'am, please
Right. So
explain it just
everybody's
once more.
happy. Do you want me to explain once more?
Please.
No problem. Okay. All right. So the idea is this: you have factorized.
I am unfortunately. Can I just
we're out of time.
1 second? I'm unfortunately going to have to run and leave you guys. The great hens are waiting for me at the moment. But thank you very much, guys. I think we're going to see you again on Thursday. Teaching Marlies the class, but I'm sure it'll be perfectly fine for you to continue with the lesson, and then I will see you all on the other side of Thursday. All right.
Awesome. Thank you, Coco. Thanks for your help.
Here's everyone.
Bye, ma'am.
Bye, Coco. All right, so just very quickly, I'll run through this again. I'm sorry I've gone over, guys. I shouldn't do that. Okay, so what we're going to do is I'm going to change these round brackets. I'm going to write a square bracket, and I'm going to take the negative out. All right, so this becomes positive theta plus 180. Is everybody happy with that? Now, the order in which I write these two terms here doesn't matter. So I'm just putting it into an order with which you are familiar, and that's with 180 first plus the theta second. Okay, so now here, what you have got, this is the same idea as this, tan minus theta. Okay, it doesn't matter that this is now a binomial instead of a monomial, right? So because tan minus theta changes to minus tan theta or reduces to minus tan theta, this also has to reduce to negative tan theta in this case. Okay, so it becomes negative tan theta. The other way that you can look at it is like this. All right. Remember, we said that negative theta was that, isn't it? Now, if I continue to go in that direction, 180 degrees, I'm going to come to rest in quadrant number 2. Okay, so if I go minus theta and then I go another minus 180, I'm going to end up in quadrant 2 where tan theta is negative. Okay, so that's 2 ways that you can look at that. All right, Matrix.
Thank you, ma'am.
No problem. So no, Cassandra, the answer is -1 because you've got a negative times a negative, which is a positive, and a positive divided by a negative is a negative. Okay, now I must just tell you very quickly before we all say goodbye, Matrix. I unfortunately won't be here on Thursday evening because I have parents' evening at my school. But Marilise is going to teach you guys. So there's just going to be 2 days where I won't be able to teach you in this particular course, but for the rest of the year, everything should be fine. Okay, so Marilise will be taking the course on Thursday. And then again on the 12th of April, I also won't be with you guys. I think that's a Tuesday. Yeah, so this Thursday and next Tuesday. Okay, anyway, if you want to go ahead and say goodbye, it's fine. Off you go. Bye. Sorry, I kept you.
Thank you. Bye.
It's a pleasure.
Bye,
Pleasure,
ma'am.
Riyadh. Bye. Bye. Is there anybody who wants to ask a question?
Yes,
You're welcome
ma'am.
to ask. Yes,
Yes,
go
ma'am.
for it, Nalwazi. Okay, so Liam, just hang on a second. Let Nalwazi go first, please. Okay,
Ma'am, I
go for
wanted
it,
to-
Nalwazi.
Ma'am, I wanted to know, how do I access the quizzes that they said we need to do at the end of the lessons? Like those quizzes?
All right, so what you need to do is you need to go and log on to the app. So you've got to get off here and go and log into the Watobe app. And then you will see, once you have actually logged into the app, it will be obvious to you as to how to find the way to the quizzes. It's very easy. You would just follow the directions to grade 12, and then you'll see when you get there, there's an option there for you to take the quiz.
Okay, thank you so much, ma'am.
It's a pleasure, Nalwazi, anytime. Okay, and then Liam, you wanted to ask a question?
So ma'am, question, when you change, if you change tan in the sum that we've just done, would it
Yes.
be minus sine over cos theta? Well, minus sine theta over cos theta.
Just say that again, Liam, please. If you change
negative tan theta, would it
Yes.
be negative sine theta over cos theta? Like positive cos theta?
It would be, Liam. Okay, now that's another thing.
Okay.
It's actually an excellent question that you are asking, because a lot of matrics make that mistake. So they see negative tan theta. All right, so they do this minus sine theta, and then they're like, okay, is it minus cos theta? And it's not. It's not, because a negative divided by a negative is a positive. So it doesn't matter where you put the negative. Either you can put it at the top, or you can put it at the bottom, or you can put it in the front, but it doesn't belong to the top and the bottom at the same time. It only belongs to either one of them. Okay, very, very good question, Liam. Well done for asking that.
Thank you, ma'am.
Okay, take care.
Okay.
See
Bye,
you guys
ma'am.
next
See you.
week. Bye.
And
Bye.
thank you.
It's a pleasure. No problem. Okay, Inam, please explain the tan part for the last time. Do you mean, Inam, do you mean the same thing that I was just explaining to Liam? I can explain that to you if you want me to. Right, so in other words, if you've got negative tan theta and you want to write that as sine theta over cos theta, because this is negative, Inam, the negative either belongs at the top Okay, so a negative divided by a positive is a negative, or it belongs at the bottom. So a positive divided by a negative is a negative, or your alternative NM is to write it in the front. Okay, but what you mustn't do, okay, well, this is wrong. So tan theta is equal to minus sine theta over minus cos theta. All right, this is wrong. Okay, because a negative divided with a negative is not a negative. Okay, so either the minus belongs to the top or to the bottom, but not to both at the same time. Okay, NM?